But we'll go ahead and just get started. If anybody else chimes in, that'll work. I just wanted to mention real quick that the activity that we introduced last time, I've made due on Tuesday because some folks were having some trouble scheduling time to drop stuff. So if you got it done, great. If you didn't, you still got some time to do it. I also took, if we look at our syllabus here and just see what's coming up, I noticed a couple of the activities were getting backed up one on top of the other. So I moved out. The measuring mass of the Earth is on Tuesday, and then our solar system will be due the following Tuesday, the same day our exam opens and we have an exam review. So on February 4th, which is not next Tuesday but the following Tuesday, we'll do an exam review and I'll open the exam in the testing center. And then that solar system's formation activity will be due then. And then we get a little break from the activities for a little bit. Just so we have time to recuperate from the exam, and then we'll get back into it a couple weeks later.
Okay.
All
Great.
right. So, go ahead, Shay.
Really, really quick, can you go over just a couple of questions really quick?
Yeah, absolutely.
On the last activity,
Okay.
the questions that ask number four, it says highest value comes from combining the highest possible height with the shortest possible time,
Right.
given your uncertainties.
Right.
How do we calculate that again?
So you're looking at the uncertainty in the times. You've got that right because that's the uncertainty you calculated right here. Is that correct?
Right, right,
Okay. So
right,
so
right.
that's okay. The other uncertainty is something you have to estimate just based on how well you think you measured the distance, right? So if I go back up to where I wrote down the distance here, and let's say, I did it at the top of a staircase that was 3 meters tall, and I used a string to drop it down the staircase, and then I measured the string using a meter stick. How well you measure that depends on how careful you were when you measured it. Did you measure it to 1 centimeter accuracy? Did you measure it to a tenth of a centimeter accuracy? Did you measure it to 10 centimeters accuracy? So, however, you just kind of have to make an estimation of how uncertain you think your measurement of the distance is.
Okay.
So, for example, when I do this, I usually can do it just because of the way it works out to about 10 centimeters or about 2 centimeters or so. So I would put in, my distance would be, I might say 2 meters, and then I would say my uncertainty is 2 centimeters, which would be 0.02 meters. And then this is the value I would use for my uncertainty. So if I was going back down here for this problem, I would say for my highest value, I would combine my longest, my highest height, which would be 2.02 meters, and my shortest time. And then for the other
Okay.
one, I would do 2 meters minus zero point zero 0.02 meters, so 1.98 meters, and my longest time. And by
Okay.
doing that, and then to
Makes
do
sense.
the same calculation again, that should give you a range to bracket those values. So like when I did the calculation, I calculated 6 meters per second squared. If I do this part, I'll probably get, my smallest possible acceleration is 4 meters per second squared, but my highest possible acceleration could be 9 meters per second squared. And so then I would write
Mm.
down, that I measured 4 meters per second squared plus or minus 3 meters per second squared. Just gives you an idea of the
Okay.
range because you can't ever measure anything with perfect accuracy.
Right.
So, so
Okay.
that's what that's for. Light is important to astronomy because it is the only thing really that we can see from stuff out in the universe. If we think about the objects that we've actually held in our hands, pieces of the moon, pieces of Mars, a couple fragments of meteorites, and collecting dust from comets. We have sampled some objects in the universe that aren't the Earth, but very very few, and we certainly don't have any samples of like a distant star or a distant galaxy. And so we're stuck with analyzing the light that comes to us from those objects. And so what we want to do today is talk about how the light the properties of the light can be examined to figure out what's going on these very, very distant objects. Because later on in class, we'll see images of galaxies back to the origin of the universe, and we're going to talk about a lot of their physical properties. And the question is, how do we even know all that stuff? We know it from the light. Um, So light is a wave. At least it can be described as a wave. It's really kind of both a wave and a particle. The wave nature of light is something that you can measure, and the particle nature of light is something you could measure. And we in astronomy typically deal with the wave description of light because we're talking about the wavelengths of light being stretched or compressed by various phenomena. So we talk about it as a wave, and this wave has a couple properties. It has the frequency of the wave, and it has the wavelength. And if we think about, I can draw this here, what a wave looks like. If I just, down here I'll put a little graph. If I draw a wave that looks like this, right, that's a wave. The frequency is going to be, if I imagine setting a little observer right here, watching this wave go by, the frequency is how fast these little peaks go by per second. So if I count the number of peaks going by, if this wave is traveling in this direction, this wave is traveling and I count 10,000 peaks go by in 1 second, then the frequency is 10,000 peaks per second, or 10,000 hertz. So that's how we measure the frequency. So the frequency is how quickly the wave goes by you, and the wavelength is just the measurement in space from peak to peak. So this is the position along the wave. The wavelength, lambda, is the distance between those two peaks. And if I take the distance between the two peaks and how fast the peaks are going by me in frequency, I get the speed of the wave. And the speed of the wave for light is always the speed of light. It's 2.99 times 10 to the 8th meters per second, and that's always the speed of every single light wave. You can't go any faster than that, and light always goes that fast. So that's just our description of light. The fact that light can be broken down into frequencies and wavelengths is really important because different physical processes emit different light of different frequencies. So if you can tell what frequency the light is you're receiving, you can tell what physical processes are going on. If we think about the electromagnetic spectrum, right, the spectrum of all light is what we call electromagnetic spectrum. The astronomers typically refer to this part right here as the visible light. So this is if I take the whole spectrum of radiation and break out this little teeny tiny piece, this is the stuff we can see with our own eyes from red to blue. And it's a very small piece of the whole electromagnetic spectrum. So when an astronomer says light, they are typically referring to the light you can see with your eyes. However, you might hear people say radio light. Radio light, or radio radiation, is long wavelength electromagnetic radiation. And if you have things like gamma rays and X-rays, those are short wave radiation. So they're all part of the same phenomenon. It's just your eyes are sensitive to this very narrow range that goes from about 700 nanometers to 400 nanometers. And just as a reminder, 1 nanometer is equal to a billionth of a meter, 10 to the minus 9 meters. So if you imagine a meter stick and cut it up into 1 billion pieces, that's a nanometer. So it's very, very, very small, and the light that your eye responds to is relatively small compared to other types of radiation, although it is a very narrow band of the radiation. And the stuff that we see here, for a long time, this is what we've been sensitive to, and only this. So if we think about astronomers since the first Neanderthal looked up at the sky and saw light, we've been working in the visible light. Back in the 20s and 30s, we developed radio and TV, and that gave us another way to view radiation in the universe. And then since then, we've been able to build detectors that can detect microwaves, ultraviolet light, infrared light, X-rays, gamma rays, all of these things. So astronomers can access the entire spectrum now. We're not restricted to just our eyes, but it's taken quite a bit to do it, and it's only been in the last 50 years or so that we've been able to see this whole thing. Part of the problem with that is the fact that the atmosphere gets in the way. Right? So our atmosphere is transparent to only some types of light, and you might not be too surprised that the main type of light that the atmosphere is transparent to is the visible. So what this graph is showing you is that if I have altitude here as a function of wavelength, I've got the visible light. What these colors mean is that if the color goes all the way down to the bottom, it means that you've reached the surface. Okay, so the atmosphere is transparent to visible light. This goes all the way to the surface, and it's also transparent to radio light, right? Because we use radio waves to transmit through the atmosphere, so it must be transparent to radio waves. So that means any sources, if I've got stars up here or galaxies of some kind, right? If they're emitting visible or radio light, they're going to be able to get through our atmosphere. However, if they emit microwaves or infrared, boop, they get absorbed in the atmosphere and you can't see it. If they emit X-rays, gamma rays, or UV, they get absorbed in the atmosphere and you can't see it. So that the fact that the atmosphere gets in the way is part of the problem, right? So if we want to have an infrared telescope, it has to be a space-based telescope. If we want a UV telescope, it has to be space-based. So that's one of the reasons why it's taken up until the last 50 years to get a lot of these data, because we had to have a space program to send stuff into space in order to see this. Okay, so let's move on to how stuff emits light. And this is kind of a fundamental property, interestingly enough, was discovered by Max Planck, who was trying to figure out how to build the most efficient type of light bulb, and he had to understand how the spectrum of the glowing filament worked in order to figure out what to make the filament out of to make it the most efficient type of light bulb, because you want the filament to be emitting most of its energy in the visible so we can see with the light. And he discovered a property of any type of matter that's called continuous radiation. He called it blackbody radiation because he had a theoretical model that if you had something that was a perfect absorber, so completely soaks up every light ray that hits it, so its color will be black, it would also emit perfectly, right? This is a theoretical construct that he had to describe the spectrum. I call it continuous because I think it's a little bit more descriptive of what the spectrum of light looks like, right? So the spectrum, the rainbow that you see when you put light through a prism, if it's coming from a black body radiator, it has a continuous spectrum. So I often call it a continuous radiation, although the literature calls it a black body radiator. So it's an idealized, perfectly absorbing body, which means it also has to be perfectly emitting because of conservation of energy. And the really awesome thing about it is that the color depends on the temperature. So the hotter something is, the bluer it is, the colder it is, the redder it is. And I'll show you a demonstration of that in just a second. I will do that now. Let's pull up a demonstration of if I take any object, and this could be literally any object. It could be a star, it could be a lump of metal, it could be a planet, it could be a rock. If I heat it up, it changes where the radiation comes out. So if you imagine a rainbow, right? So this is a rainbow of light, and we're going to imagine a rainbow but flip it on its side so that we're going to draw a plot as if the height of the plot is how bright the different colors in the rainbow are. That's what we're showing here. We've got a plot of intensity on this axis. So this is the intensity, and we have the wavelength on the x-axis. So that what happens when you change the temperature, and I'll put this website online for everybody, what happens when you change the temperature by sliding this bar back and forth is that the spectrum switches back and forth so that the peak occurs at a different wavelength. So this peak right here is telling you where the most radiation is coming out of this glowing object. And if I make the object hotter, the peak shifts to the left, so it gets bluer. Up here is showing you what the object would look like as its color. And if I shift it to the right, it gets redder. And it shifts back and forth as I change the color. And the great thing about this is it's totally dependent on just that temperature. So if I look up in the night sky, if you go out in the night sky tonight and you see a red star next to a bluish white star, you know the red star is cooler than the bluish white star just by looking at it. You don't need any special equipment or anything, which I think is pretty exciting, that you can just look at stuff and see what the temperatures are. So that's the black body radiation that that all the stars emit. And if I look at that on our graph here, we can see what different types of stars have as far as their colors. So if I look at the sun is a 6,000 degree Kelvin star, that's this one right here, you see that this peak wavelength is right at about 500 nanometers, which is the same as the peak sensitivity of your eyeball, and that's not by coincidence. Our eyes evolved under a planet with sunlight from a sun-like star, so of course our eyes are going to be most efficient at the wavelength that the sun emits the most light, right? So this is a sun-like star. If I go to a hotter star, say a 7500 Kelvin star, that's this guy up here, that is shifted to the blue, right? So a blue star is going to be warmer, and therefore it's going to be bluer, right? This is a little bit different from what you're used to. We normally think of blue being cold and red being hot, and that's because fire is red and water is blue. But in terms of the black body radiation, it's opposite. Hot things tend to be bluer or even blue or white. And if I look at something really cold for a star anyway, I see this guy right here. It's at 4,500 degrees Kelvin, again shifted. The stars get brighter just overall as they get hotter because they are larger stars and emit more radiation, but it's this peak that shifts from one end to the other. Now you are a continuous emitter as well. You have a temperature of about 300 degrees Kelvin, so it's way over on the, if you think about this peak shifting, 300 degree Kelvin peak is going to be down here in like the far infrared, and you would look like this. So there's your continuous spectrum right there. You can feel the heat coming from your body. You are a continuous emitter, and if we were to put you out in space, we could detect you with an infrared telescope. So I want to write this down mathematically as well, because astronomers like to be able to calculate the actual temperature of something, not just the temperature differences. And we have a rule called Vess Law. And Wien was a scientist who empirically worked this out. It was Max Planck who worked out the total theory. But he discovered if he just took different filaments and he measured the temperature of the filament, then measured the peak wavelength from the spectrum, he got this relationship where they were inversely proportional. So he found that if I were to measure the wavelength in angstroms, which is 10 to the minus 10 meters, so the wavelength in angstroms is here, then if I divide that into this number, this constant, empirical constant that he discovered, I get the temperature. So for example, let's take the sun. The sun has a peak wavelength, lambda max, 500 times 10 to the minus 9 meters, 500 nanometers. We need this in angstroms, so I'm going to have to take 500 times 10 to the minus 9, which is going to give me 5,000 angstroms. So if I put 5,000 down here and divide it into 2.9 times 10 to the 7, so I take 2.9 times 10 to the 7 and divide it by 5,000. That should call up my Google calculator, and I get a temperature of 5,800 degrees Kelvin, which is what we saw from this plot. We have about 6,000 degrees Kelvin. But the cool thing about this is now I can build an instrument called a spectrometer that I go outside and stare at a particular star. I can get the spectrum of light from that star, precisely measure the peak of that spectrum, and calculate the temperature. And that's it. That's all I have to do. And this is incredibly powerful because it's independent of distance, it's independent of composition, it's independent of when you look at it, right? It's just a measurement you can make, and it's a fundamental property of the star, how hot it is. So that's really exciting. But it gets a little bit better, because if I have a hot object, I'm going to just draw a hot object here. Okay, so if I have a hot object like a star that has a certain temperature, T, right? I can ask myself how much radiation is coming off of every single little piece of this star, right? So if we've got something hot, I can calculate from its temperature how much energy is coming off it. And this is something we call the flux, right? So the amount of energy coming off of this is called the flux. And it has units of energy, how much total energy is coming out per square meter, right? So how big of a piece of area we're talking about per second. So how fast is it coming out? And this energy is directly related to the temperature, this flux, right? This flux of energy coming out, which is the energy per every square meter per time, tells you how much total energy is coming out of that object, just from measuring the temperature. This law is known as Stefan Boltzmann's law, and Stefan Boltzmann found that if you went and took the temperature that you measured from this spectrum and multiplied it by a certain constant, and that constant is something we had to discover empirically in the laboratory, but it's a known physical parameter. That constant multiplied by the temperature gives you this flux. Again, this flux is in energy per meter squared per second. Okay, so just a simple measure of the temperature tells you the flux, which is amazing, right? If you think about it, the fact that the temperature is so easy to measure using a spectrum and it gets you this really fundamental parameter. The really cool thing is that if you notice, right, this little thing right here, if I somehow knew the area of the star, how big it was, right, I could tell the total emission, right? The total emission from the star, because if I've got a star and I've just measured the energy coming out of this little bit, but I knew how many little bits there were all around the star, each emitting this Stefan Boltzmann radiation, right? If I could just count up how many of those there are, I could figure out the total emission from the star. And the total emission of the star has a name. It's called the luminosity. And the luminosity is something we can directly measure. So we can relate the temperature, which we can directly measure with using the spectrum, to the size, to the luminosity. And it's amazing that we can do this, right? If I put all that together, so if I put all that together, I get the luminosity on this side. Luminosity on this side, that is the intrinsic brightness of the star, how much energy per unit time is coming out. Energy per unit time. And I compare that to measures of the temperature, right, which we get from the spectrum. Then I can determine the size, the area, the surface area of the star. So two things I can measure, luminosity and temperature, tells me the size. I never have to visit the star, I never have to go there, but I can figure that type of stuff out. So this continuous radiation is amazing that we can do this, that I can tell you, as long as I can measure the luminosity and temperature of an object in space, I can tell you its size, which is cool. Okay, so just to review that, the color tells you the temperature, right? The temperature tells you the energy, the flux coming out. The total energy tells you the size, and those together, the total energy and the size determine the luminosity, so that if you can measure the luminosity and temperature, you can measure the size. It's just a fantastic property of glowing objects. And so I can sit here at my computer with my telescope on the planet Earth and understand the entire universe. It's one of the most powerful things about the science of astronomy, that light lets you do this. There's a couple of other features of light that we're going to get into a little bit later, how we break up the spectrum. The spectrum also can tell you things like composition, because different atoms in the spectrum have different compositions. Or, sorry, let me put it another way. Different atoms have different spectra that they emit, and so if I have a particular atom in the star, I can tell that it's there by the spectrum that it emits. We can also tell what's there by what we don't see. If we have a bunch of atoms that are absorbing a particular wavelength, we can tell that just by looking at the spectrum. So composition is something we can tell from the spectrum, and then we also use the spectrum to determine the motions of the stars, right, in terms of their Doppler wavelength shift, which we'll talk about when we get to exoplanets. So you can tell a lot about stuff about a spectrum. You can tell pretty much everything except the mass of the star. That's a tricky thing to measure, but we'll talk more about that when we talk about using gravity to measure the motions of stars.
So how do you determine with the one that says the total energy and the size determines the luminosity?
Mm-hmm.
So you're only taking a certain part of the star as the size?
Oh yeah, so I'm taking the whole star. So this is so if I look at the the star, let me just draw it here. If I look at the star itself, what the Wien's law tells me is that if I can measure the wavelength, I know the temperature of the star, and the temperature is a property of the whole star, right? Like the whole star has a single temperature. So the temperature only tells me how much radiation is coming from every little square meter of the star. So if you imagine, the star has a temperature T, but if I were to take a chunk of that star and move it out all by itself, it would still have a temperature T, right? So the temperature can't really delineate what the absolute size of the star is because the star has the same temperature all over its surface. But what it can tell me is how much energy is coming out of every little bit, right? So
Right.
what the temperature tells me is how much energy comes out of every square meter of the star in a given amount of time. So that was the Stefan Boltzmann law, that this energy coming out of every single little bit, and it's this bit over here, this bit over here, this bit over here, every single little bit of it is this sigma t to the fourth. And this energy has units of energy per square meter per time. And I'll put seconds down there. So what that means is if I want to know what the total luminosity is, which is the amount of energy per time, I just have to multiply this by the total area of the star. So that means if I know all of the all these little bits of the star, the surface area adds up to the surface area of the whole star, right? The whole surface is emitting.
Right.
Then if I were to take this energy I get from the temperature and multiply it by the area, then I get what's known as the luminosity, which is just the energy per unit time. So the luminosity, L, is the energy per time. So I multiply by the area and I get rid of that per meter squared, and it just gives me the luminosity. And you've heard of luminosity, the units we use are watts. And so you've
Right.
seen that on a light bulb. If I look at a 100-watt light bulb, that's telling me that I'm getting 100 joules of energy every second, or 100 watts, right? If you wanted to figure
Right.
out, you could probably, it occurred to me, we could probably do this experiment if we had spectrum glasses, because what you could do is you could look at a light bulb and see where it peaks uh, in the wavelength. So let's say you look at a light bulb and it's yellow, right? So
Mhm.
yellow is about, let's say, for sake of argument, 500 nanometers, right? So you look at this yellow light bulb and it tells you that it's 500 nanometers, which is about 6,000 degrees Kelvin temperature. That's the temperature of that filament. So then if you could figure out what the uh, area of that filament is, right, you could multiply that by sigma t to the fourth right here, and you could get the luminosity, but you already know the luminosity, so you can actually calculate the area of the filament. So it's a diagnostic that if you have this relationship that says luminosity is equal to this property right here, remember, is called the flux, times the area. Area. So if I can measure the luminosity, or if I can read on the package that it says 100 watts, and I can measure the flux, which I can do because I know the color, which tells me the temperature, then I can determine the area. That's the thing you don't know. And that's what we do with stars. We take our telescopes, we measure how bright they are, we measure their temperature using the spectrum, and the temperature gives us the flux, the brightness gives us the luminosity, and from that we can get the area. And the area is the total area of the star.